Okay, here we are back to finish off chapter 16. So when I left off in the last one, I was talking about this percent ionization. So I think I want to go back and just give you a little bit more on this um, because it is an important aspect. There's this rule when you're talking about determining these equilibrium concentrations for weak acids and weak bases that if you exceed what we call the 5% rule, um, then you have to consider the X. But if it's less than 5%, as it was here, in my example, we didn't have to consider what that X actually means. So let me just talk about what that 0.77 means. So if in my example where this side of my equation becomes my plus X along with the hydrogen ion, and this side of my equation becomes the minus X, then in, say, the ice chart in the change row, then when I put it into my equilibrium expression, my anion and my hydrogen ion are going to be my two unknowns. And this, which was originally at 0.3 molar, the original information given, so that's going to go down by an amount of X. And so in order to find out what X is, I'm going to have to set it equal to 1.8 times 10 to the negative fifth, which is the given for this ionization of acetic acid. So if I go through and I just ignore the X for a moment, which I've done here, and I solve for my pH, I find my pH to be 2.64. Then I need to look at my percent ionization. My percent ionization comes from the amount that X is, which when I solve for my X in this problem, is 2.3 times 10 to the negative third, out of the total amount of the original molarity times 100, I find out it's 0.77. So what that tells me is that the amount that this original 0.3 goes down by is not significant enough in this problem to have to consider it here. But if for some reason this were at 5% or above, then that's the cutoff. When I do my initial solution just by simple math, simple algebra, ignore that. If I do the percent ionization and I find it's over 5%, then what I need to do is go back here, consider this X in my algebraic manipulation, and I'm going to end up with a quadratic form of the equation. So I'm telling you that only because it's important to know for time considerations in terms of solving problems on a test. I'm going to not make you be required to solve one of these using the quadratic, but just so you know, if you further your studies, that 5% rule is something that needs to be considered. But again, I will not hold you to solving ones that require the quadratic. Okay, and then the next piece of this deals with a weak base, and the weak base will behave similarly to the weak acid. You're going to have the base, that's just a generic notation for a weak base, B plus water. It will react with the water and give you the hydrogen attached to the base and releasing the hydroxide. So it's the presence of the hydroxide that's released that gives it the base character. So then I would go through and I would set up using the Kb expression, just like a Ka expression or an equilibrium expression, where I'd have my two products over my original reactant, again, leaving out the water. You leave out pure liquids and solids. And then I just ran through and did it using the example of NH3, the weak base, showing you what your expression would actually look like. And then what you would do, plug in the KB value, that would be a given, and then solve x times x, solve for whatever that would be. And then again, that same idea of ignoring that amount that it goes down by because it's so small. As I said, I'm going to make sure that all your problems, we can ignore that, not worry about the 5% rule. And then solve for whatever your OH ion is. That's what you'd be solving for here. These would be your X and your X. You would solve for that X here as the hydroxide ion. Once you find the hydroxide ion, you would then do the POH from the hydroxide, and then from the pH calculate, from the POH go to the pH. So what would that part of the problem look like? It would be to find the POH, you would just take the negative log of the hydroxide ion, which would be that 1.6 times 10 to the negative third. Then once you calculated the POH, you could find the pH, because we know that the POH plus the pH is equal to 14. Okay, stop there for a minute. And